Okay, so far what we've been talking about is the nuclear decay equations that are what we use to describe exactly what's happening to the nucleus of the atom. So we wrote down some for alpha, and we were paying attention to subtracting 4 and subtracting 2. And then we wrote some down for beta as well, where we were making sure that the atomic number, the number of protons, went up by 1. And the beta ones were a little bit harder than the alpha ones, because with alpha we had the 4, 2, and that really meant 2 protons, 2 neutrons. But with the beta we had the 0, -1, and that was more of a little bit of abstract notation, really, just to make sure the sums worked. You can't really have 0 protons and neutrons in an electron. It doesn't really make sense. What we're going to do today, though, is not ask what happens, but when does it happen? So we just need to have a little look at some words for that. So let me share the PDF with you. Okay, just have a little read of that. I'll give you 30 seconds to read down to where it says number 1. Okay, so what you've just read is that different nuclei are more or less unstable. So obviously the gold star here comes for all the atoms that are completely stable. They have exactly the right number of neutrons to hold on to their protons, and that nucleus will last forever. But for the nuclei that have the wrong number of neutrons, the question is, how wrong are the number of neutrons? So for instance, if you had a nucleus that had 100 protons and it needed, for the perfect number, I don't know, 150 neutrons. Well, any number that's not 150 will be the wrong number of neutrons, and it will be unstable. But maybe there's a whole range of instabilities. So maybe 151 neutrons, just one too many, isn't that bad. Maybe the nucleus can live with that for quite a long time. But maybe 160 neutrons or 140 neutrons with a difference of 10 from this perfect number, maybe that's really bad. And maybe that makes the nucleus really, really unstable. So isotopes come in a range of how radioactive they are. Some of them are almost not radioactive at all, and they can practically last almost forever, millions of years before they decay. Other ones might be so unstable that they might last for microseconds before they decay by releasing an alpha particle. That's what today's lesson's about. It's about when will the nucleus decay, and it's related to just how unstable it is. So let's have another look down the list, further down the booklet. Okay, have a little look at those two definitions, words 1 and 2. So I'm looking for your literacy now, or your vocabulary. Do you know a word that means happens for absolutely no reason at all? Anybody have a clue for a word that means that? Happens for absolutely no reason at all.
Random.
Okay, random is a good word, but it's not the word that means this. Oh, George, I like it. On the chat. Okay, spontaneous. If you have a spontaneous friend, it means they just do things for seemingly no reason at all. So you ring them up one day and they say, I'm wearing a banana on my head. And you think, why would you be doing that? And it's just spontaneous. They're just doing it because they want to. So number 1, when you get your booklets next week, you're going to have to write the word spontaneous on that line next to number 1. So just jot it down in the back of your exercise book now. So we believe that radioactive decay of nuclei is a spontaneous process. That means that nothing causes it to happen. Now, that's a really weird idea because usually there are causes for things. So if you hear a banging sound, it's probably because someone's just dropped something on the floor. The book hitting the floor caused the banging sound. If you stub your toe and you feel pain because you stub your toe. Causes tend to have effects, and effects have causes. What we're saying with spontaneous nuclear decay is that there is no cause, that the alpha particle is emitted from the nucleus for no reason at all. It went for days, weeks, years, months, thousands of years with nothing happening, and then one day, 1 second, for no reason at all, the nucleus decided, this is my moment, and it throws out the alpha particle. We think maybe radioactive decay might be the only spontaneous process in the entire universe. It is a weird idea to think that something happens for no reason at all. So that's the word spontaneous. The key thing that I want you to take from the word spontaneous is if it happens for no reason at all, then there's nothing we can do to make it happen. So if I give you for Christmas a kilogram of uranium, which is radioactive, and you don't want it to be radioactive, you think, what a rubbish present. Who would give someone a radioactive kilogram of uranium for Christmas? You'd like to keep the uranium, but you don't want it to be radioactive anymore. You'd like it to get all the radioactivity out of its system. So you think, oh, I'll hit it with a hammer, I'll set fire to it, I'll send it to the moon, I'll boil it in acid, I'll paint it green, I'll send it to the bottom of the ocean, I'll put it in my freezer. There's nothing that you can do to it that will make the radioactivity happen faster. There's nothing you can do to make the atoms decay and turn into stable elements instead. You can't do anything about it. So keep that idea in your head. Radioactivity proceeds at its own rate, never faster, never slower. It always goes at the rate it wants to go at, and there's nothing that we can do about it. Hold that thought in your head. Okay, word number 2. This is a word that means that something is governed by probability. So this is like tossing a coin. It might come down heads, it might come down tails. That's 50-50 either way. But when you do toss the coin and it lands either head or tails, the outcome is, what word would you just use to describe that? We have actually already heard it once today.
Random.
Random, very good. So this is the word random. Random refers to things that happen through probabilities. So if you roll a dice, every number on the dice has a 1 in 6 chance of coming up. So you throw the dice, and does it come up 5? Well, maybe it's got a 1 in 6 chance of doing it. And whatever the outcome is, it's random. It's governed by probability. So we think that nuclear decay is governed by probability. So if you look at a nucleus, it might have a decay or it might not, but it's definitely got a probability of decaying every single second. So you might be looking at a nucleus through a very good microscope, and you'd be watching it for the first second. Did it decay? Second second, did it decay? Third second, did it decay? Fourth second, oh yeah, it did. But each second, it's got a probability of decaying, and that probability does not change. So let's just pretend it's 1 in 6. So you watch the atom for the first second, and there's a 1 in 6 chance it decays. So 5 times out of 6, it won't. 1 time out of 6, it might. Pretend it doesn't. So you watch it for the second second. It's still got a 1 in 6 chance of decaying. Just because it didn't decay in the first second does not make it more likely that it will decay in the second second. It's still 1 in 6. So it doesn't decay maybe, so you watch it for a third second. The probability is still 1 in 6. It doesn't get more likely just because you watch it longer. Okay, that's random and governed by probabilities. Now, if I did give you a kilogram of uranium and you sat watching it, and let's pretend the probability is 1 in 6, it's probably not. Uranium isn't very radioactive, so it probably has a much lower probability than that, 1 in 60 million maybe. But let's just go with 1 in 6. You might have a few billion atoms and you watch them, and they've all got a probability of decay of 1 in 6. So you watch them for a second, and I don't know, maybe a sixth of them decay. And you watch them for another second, maybe another sixth decay. But the point is, you can't guarantee that they will or won't decay. So it's not like you can come back tomorrow and say, you know what, they'll definitely all be gone by tomorrow. Because what happened the previous second, minute, hour, month, it doesn't make a difference to the future. It's always 1 in 6, which means you can never say for certain when it will finish decaying. You can't say forever that my thing, my Christmas present that's rubbish, my radioactive uranium, you can't say it'll not be radioactive next month or next year or in a million years. You can't say it because you just don't know. It's always a 1 in 6 chance, and maybe that just doesn't happen. So you might think that we can't answer the question, how long will something be radioactive for? How long does it take for the radiation to go away? But that's not quite true. But in order to see that, we need to do a little experiment. Now, if you were in school today, sitting in this room in front of me, I would have a little pot of 100 dice for each of you. And you'd have a little tray to throw it into, and you would throw 100 dice. And that would be like 100 radioactive atoms. And each one would have a 1 in 6 probability of decaying. So you'd throw the 100 dice, and then you'd hunt through, and you'd take out all the ones that came up, I don't know, 6. And they would be decayed atoms. And you'd put them to one side because they've decayed and we're not interested in them anymore. And then all the ones that were left, you'd scoop back up into your pot and you'd throw them again. And you'd throw them again and again and again and again until you ran out of dice. Unfortunately, you're not here in this classroom with me, you're at home. So we're going to have to do the next best thing, which is a little bit boring, but we'll go with it because it won't take very long. Let me show you something else. Okay, here is a simulation of 100 dice. So you can see that these dice have been thrown and that some of them, 8 of them, have come up as a 6. So these represent our decayed atoms, our decayed nuclei. So there's a 1 in 6 chance every second. Let's pretend 1 second has just gone by. So we began with 100 undecayed atoms, and we just lost, what, 8 of them. So let me just get rid of these 8. So get rid of those. Oops. Sorry. And now we're down to 92 atoms. So imagine that I've just thrown the 92 dice back into the tray again. And this time, loads of them have come out 6s. Remember, it's random. So sometimes we're going to get a lot, and sometimes we're not going to get very many. So this time, it seems we've just got a load. So I'll get rid of those. So off they go. And now we're down to 76. And they've been thrown again. And there they are in their 6s. So let's get rid of some of those. Now, roughly each time we do this, ish, because it's random, so we can't be sure, roughly we would be expecting to lose around about 1/6 of the atoms each time, because roughly 1/6 of them are going to come up 6, because every single one of them has got a 1 in 6 probability. So it's not going to be exact, but bit by bit by bit, we start to lose our atoms. And if we keep track, every second, of how much radioactive stuff we've got left, it will get less over time. It's not possible to say how long it'll take until none of it is left, but you can certainly see that the radiation is going away. The radioactive atoms are decaying, the alpha or beta particles are coming out, and what's being left behind are stable atoms that are no longer radioactive. Now, at the beginning, when I had loads and loads and loads of atoms, I had loads and loads and loads of decay, because a sixth of a big number is a big number. But as time goes on, I've got fewer and fewer and fewer atoms, and a sixth of a small number is a small number. So at the beginning, we were losing 15, 20 atoms at a time. We're just losing 4 at a time now. In fact, that time, I haven't lost any at all. None of them came up 6 that time. So throw it again. Okay, 2 of them this time. 9. And then 1 of them this time. 2. Now, even though we're down to like almost none at all, forgot one. Even though we're down to almost none at all, it's still not possible to say when these last 5 will go away. Sorry, got to get rid of it. Because there's a 1 in 6 chance every time. And we just don't know when the 1 in 6 will come up for the last 3 now. Oh, we've lost 1 that time, down to 2. So 1 in 6 chance down to 1. So that one hasn't decayed that time. And now we could sit here for go after go after go until it finally turns into a 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 17 throws until it finally went. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 until it went. You just can't say how long it will be until the very last one goes. So what I'm trying to demonstrate to you here is that it's not possible with a spontaneous random event. It's not possible to say that it will finish after a certain amount of time. However, something is possible. So let me show you this instead. Hang on a minute. Okay, so these are the results from my class last year who were in school and did manage to do this experiment. So we got a little bored after throwing the dice 30 times. So I told them all to stop after 30 throws. But can you see that group number 1 in the first column, a bit like I've just done on the board, they got down to 1 last atom and it took forever to get rid of it. In fact, by the end of 30 throws, they still hadn't thrown a 6. Whereas if you look at group number 6, they only needed 12 throws to get rid of all their dice. It's completely random. One group's lot of 100 pretend dice atoms lasted for a lot longer than another group's 100 pretend dice atoms. Radioactive decay is random, and you can't predict how long it will last for. But I had 13 groups in the class, and they all threw 100 dice. So between them, they actually had 1,300 pretend radioactive atoms. And it turns out that if you lump them all together, so that you're dealing with not 100 dice, but over 1,000 dice, the statistics start to even out. When you do something random a couple of times, anything could happen. But when you do something random thousands and thousands and thousands of times, the probabilities just start evening things out. If you throw one dice 6 times, you are not guaranteed to get a 1, a 2, a 3, a 4, a 5, and a 6. Even though they have a probability of 1/6 each, if you only throw it 6 times, you're very unlikely to get all of the numbers come up, each a sixth of the time. But if you throw a dice 1,000,000 times, you would expect the ones to come up roughly a sixth of the time, and the 2s and the 3s and the 4s and the 5s and the 6s. Probabilities have a way of evening themselves out when you deal with really big numbers. So take a look at the graph on the right-hand side of the screen. The graph is showing you what happens when you've got big numbers. And you can see that they line up and make a really convincing pattern. You could draw a line of best fit through that and it would be very smooth and very lovely. And in fact, if you were in class, that's what I would be wanting you to do. In fact, in the booklet, there is a blank page ready for you to put a graph in. So let me just switch back to the booklet. So there's your empty graph that you were supposed to be drawing today. So what does it look like when you put the line of best fit on it? It's this lovely, lovely curving dashed line that's on there. And it's a really nice pattern that doesn't really have any anomalous points on it. When you deal with big numbers, probabilities have a way of evening themselves out. Notice the graph never really gets to 0 because it's not really possible to pin it down and say how long it'll last. But take a look at the dashed lines that I've put on the graph. Let me explain what those are. Let's just notice that we begin with 1,400 dice on this graph, 1,400 atoms, nuclei that are radioactive that have a 1 in 6 chance of decaying. Let's ask ourselves, how long does it take, not for all of them to go away, because we can't say that for sure, but how long does it take for half of them to go away? So half of 1,400 is 700. So I've drawn a dashed line going across from 700 until it hits the graph. And then I've dropped it down onto the throws axis or the time axis. And I've asked, how long did that take? And reading from the graph, it took 3.7 throws on average. So somewhere between 3 and 4 throws for half of the dice to go away. When I'd thrown the dice 3 times, I still had a bit more than half left. But by the time I'd thrown the dice 4 times, I'd gone past the halfway line. I'd thrown out half the dice because half the dice had landed up on 6. So now I've got 700 dice left. Well, let's use the graph and find out how long it takes to get rid of half of those, to get rid of 350 of them. So we go down on the graph, on the axis on the left-hand side to 350, and we draw the line across until it hits our graph, and then we drop it down, and wow, look at that. It takes another 3.7 throws to get rid of half of what I had left. Let's halve it again. So I've got 350. Let's halve that down to 175. How long does it take to get rid of another half? So to get down to 175, go across and oh, wow, look at that. Another 3.7 throws. Let's halve it again down to 85 or something like that. And oh, look, another 3.7 throws. Now, I don't know how long these 3.7 things are going to go along until I've got none left. But it does seem to be the case that every 3.7 throws, however many atoms I've got left, I lose half of them. Now, people sometimes think this is a bit weird, that I lose 700 in the first 3.7, but I only lose 350 in the second 3.7, and then I only lose 175 in the next 3.7. But remember, when you've got a lot of atoms, you're going to lose a lot of atoms because there's a lot of them to decay. When you've only got a handful of atoms left, you're only going to lose a couple because you haven't got that many that could decay. So it is going to slow down. When you've got a lot, you're going to lose a lot. And when you've got a little, you're going to lose a little. So don't get hung up too much on the numbers. Just focus on what the graph's telling us. It's telling us that however many atoms we've got, you lose half of them in a fixed amount of time. This amount of time is directly related to the probability. So for dice, for 1 in 6, the time is 3.7 throws, or if it was atoms, 3.7 seconds. If I were to use a dice with a different number of sides, or a coin with 1 in 2 sides, things like that, the probability would change and the 3.7 would change. This is just because we did it for dice. The probability for atoms depends on how unstable the nucleus is. So some isotopes are really, really unstable, and they've got a really high probability of decaying. In which case, this 3.7 would get smaller and smaller and smaller. And for really unstable atoms, it might turn out that this number is microseconds. For atoms that are quite stable, they'll have a really large, very small probability of decay. And so they're going to have a really big number. This number is directly related to how unstable the nucleus is, and every isotope is different. But even though each isotope is different, every atom of that isotope is the same. Because of that, we've given it a name, and we've called it the half-life. It's the half-life time. It's how long it takes for half of however many atoms you've got to decay. Now, I have absolutely no idea which atoms will decay in particular. If I give you 1 million atoms, I can promise you that 500,000 of them will have decayed in, I don't know, 3.7 seconds. I won't be able to tell you which 500,000, just that it'll be roughly half of them, 1 in 2. Every other atom will have decayed, every other nucleus. Let's have a look at some examples to make it a bit more concrete. So here are some isotopes taken from the periodic table. So you should recognize these names: lithium, krypton, sodium, iodine. These are all names of elements off the periodic table. And all of them have a stable isotope that isn't radioactive at all. But these isotopes in this table, these are not those. These are isotopes that are unstable. They're radioactive. They're going to decay. The question is, how quickly will they decay? How long will it take to decay? Well, I have absolutely no idea how long a sample of lithium-8 will last for. No idea at all. It's not possible to work it out. But I do know that on average, I will lose half of it every 0.8 of a second, because it's really, really unstable. And it's decaying very quickly indeed. It only takes 0.8 of a second for half of it to decay. Half of it will be left over though, and I'll have to wait another 0.8 of a second, but I won't lose it all. I'll just lose half of what I've got left. So after a second 0.8 of a second, I'll be down to a quarter. After another 0.8 of a second, I'll be down to an eighth. After another 0.8 of a second, I'll be down to a 16th. And I don't know how long I'm going to need to halve this until I'm completely out. But I do know that halving takes 0.8 of a second. Lithium is particularly unstable. it has a very short half-life. But as you go down this table, notice they're getting more and more stable. So krypton-89, we're up to minutes. Sodium-24, hours. Iodine-131, we're into days. Cobalt-60, that's the one I had in class, the one that was giving out gamma rays, 5.3 years. Now, I've had that source actually in school for about 15 years. So how radioactive is it now compared to when I had it? Well, it's halving every 5 years. So after 5 years, it was half as radioactive. After 10 years, it was a quarter as radioactive. And now, after 15 years, it's only an eighth as radioactive as when I bought it. Now, luckily, it was pretty radioactive when I bought it, but an eighth is actually getting on for losing. I've lost 7/8 of my radioactivity. So when I do experiments with you guys in class, it's not as radioactive as it used to be, and it's not as impressive as it used to be. I might keep it for maybe another 5 years until it's down to a 16th. But after that point, I might think, you know what, even though it's still a little bit radioactive, it's not good enough for science experiments anymore, and I might need to buy a new one. Radium-228, 1,600 years for half of it to decay. It's not that radioactive. If you held it in your hand for a few minutes, very, very, very little radiation would come out because it's taking 1,600 years for those atoms, half those atoms to decay. Not many would decay in a couple of minutes. But uranium-235, look at that, 700 million years. So if I did give you a Christmas present of a kilogram of uranium-235, in 700 million years, your descendants, passing it down as a family heirloom, would still have half a kilogram of it left after 700 million years. Right, the concept of half-life is a hard one. It just doesn't fit right in the human brain. It's hard, and it doesn't feel like it behaves the way it does. Most people tend to think, well, if I've lost half of my lithium-8 in 0.8 of a second, then I'll lose the other half in another 0.8 of a second, which means it'll all be gone in 1.6 seconds. Doesn't work like that. You don't lose half and then the other half. You lose half of what you've got. So you lose half in the first half-life, but then you lose half of a half in the second half-life. And you lose half of a half of a half in the third half-life. It's always half of what you've got left. So let me show you a common exam question that comes up often on papers. So let us, I need to rub that out. Hang on a minute. Let's pretend that I have got, I don't know, 32 grams, I probably don't, 32 milligrams, that's more like it, of my cobalt-60 when I bought it. Say I bought 32 milligrams of my cobalt-60. So after 5 years, I only had 16 milligrams of it left because it halved in 5 years. The half-life is 5 years. After another 5 years, I've only got 8 milligrams left because half of 16 is 8, and it halves every 5 years. After another 5 years, I've got 4 milligrams left. After another 5 years, from today into the future, I'm only going to have 2 milligrams left. When you're answering questions about half-life, it's really, really useful to write it out like this as a chain of halvings with the half-life written on each arrow. Always the same half-life because it never changes for any particular isotope. If this is cobalt-60, it'll always have a half-life of 5.3 years. never changes. That's the number that we've measured for cobalt 60. The crucial point is half, half of a half, half of a half of a half. It's always a fraction each time. Now, because this is tricky, and because you definitely need to practice this, I have got some questions for you that I'm going to put on the screen now. So let me just do that so you can have a look at them. Okay, now that's probably a little bit small on your screen. I wouldn't expect you to be able to read that the way it is, but I've put that PDF onto Google Classroom so that you can download it yourself and you can open it yourself and you can zoom into it yourself. What I would suggest you do is that you read through it, the text bit and the notes and the key points, and then if you want to make any notes in your book, you can do that. But at the end, there are, what, 4 questions? I'd really like you to have a go at those 4 questions to see if you understand this concept or not. So this lesson's going to go on for another 20 minutes. Is that right? Yeah, 20 minutes, 25 minutes. I'm going to leave the Google Meet on. I'm not going anywhere. And after a little while, I'll put some of the answers on the board so that you can see what they are. But what I want you to do now is switch to the book and try and do those 4 questions. But like I say, if you want to do a little bit of reading or a little bit of note taking first, that's fine. You got 25 minutes. I'll put the answers up in about 10 minutes, or start to put the answers up. And if you're stuck or you're confused, just unmute yourself and ask me any questions. I'm not going anywhere. Stay in the meet, please. Please don't leave. You don't have to be sitting in front of the screen now. You can switch to your book and switch to that PDF and start doing the questions. Okay, have a go. Let me know if you get stuck.